Hello and welcome to this lecture on advanced electric drives. In the last lecture, we were discussing about a cycloconverter fed synchronous motor drive with unity power factor operation. As you know, the synchronous machine has a field winding. In case of a wound full synchronous machine, we have a field winding, and the synchronous motor can operate in leading power factor, in unity power factor, or in lagging power factor. As a special case, sometimes it is beneficial to operate the machine under unity power factor condition. That is what we are discussing in the last lecture. The advantage of operating an induction synchronous motor under unity power factor operation is that it only takes active power. The power is only active, there is no reactive power. Hence, the efficiency of the overall system is maximized. So, if we see the block diagram that we are discussing in the last lecture, in the block diagram we have the cycloconverter. This is the cycloconverter that we have, and the cycloconverter is feeding the armature of the synchronous machine. This is the armature of the synchronous machine, and the field winding is fed from a different converter, that is a 6-pulse converter which is feeding the field winding. And the cycloconverter, if we see, this has got two antiparallel bridges of converters in each phase. Phase A has got a positive SCR bridge and also a negative SCR bridge. Similarly, phase B has got a positive SCR bridge and negative SCR bridge, and phase C also has a positive SCR bridge and a negative SCR bridge. Now, in each phase the current is alternating, and hence we need two converters, one for the positive current and one for the negative current. In fact, we need two bridges. So, per phase we have two bridges, one for feeding the positive current and other for feeding the negative current. And the field winding is fed from a separate 6-pulse converter, that is what we are talking about in this case, and the whole system is operated in such a way that the power factor is unity. Now, how is the power factor unity? That we can just see by referring to the phasor diagram that we have already seen in the last lecture. So, in this case, you know that this is the magnetization current Im, and the magnetization current and the armature voltage Va are perpendicular to each other. This angle is 90 degree. So, since this angle is 90, Ia, which is also having 90 degree with Im, is in parallel with Va. This is Ia and this is also Ia. So, in fact, what we have two lines which are parallel, Ia here and Ia here, because these angles are 90. We have 90 degree here, also 90 degree here. So, as a result, we can see that the current Ia is in phase with the armature Va. So, which means the power factor is 1, power factor is unity, or theta, the power factor angle, is equal to 0. So, to impress this particular condition, we have to control the field current as per this equation. The field current If is if you see this right angle triangle, one side is Im prime, the other side is Ia, the armature current, and the third side is If. If is along the field axis. So, we have the field poles here, this is the field pole. So, If is along the field axis or the D. So, this triangle, one side is If, other side is Ia, and the third side is Im prime, and Im prime is the magnetization current. Now, to ensure that this right angle triangle exists, we can find out If by this relationship. So, If is given as Im prime by cos delta. Now, what is this delta? This delta is the torque angle. Delta is this angle, which is the angle between the D axis and the stator flux. The stator flux is along the magnetization current. The stator flux is Is, This is the stator flux linkage, and the stator flux linkage is along the magnetization current direction. Angle between the stator flux linkage and the d axis is the torque angle. Now, if we want to find out the reference field current, it means when the synchronous machine is operating, we have to adjust the field current. The field current has to be adjusted in such a way that the power factor is maintained at unity. So, in other words, the field current IF is controlled as Im prime by cos delta. So, this delta has to be found out, and to find out delta, what we need a torque angle estimator. So, this is a torque angle estimator which is a block in this particular block diagram. It is a computational block, and out of this we get the torque angle, that is delta, and the torque angle is fed to this calculation block, and we get the reference field current as Im prime by cos delta. So, what is this torque angle estimator? So, the torque angle estimator takes the input as the Ia, the armature current, Ib, the armature current is phase B. Since we have, let us say, assume a star connected machine, if we know Ia and Ib, we can find out Ic. Ic is equal to minus of Ia plus Ib. So, in fact, we can calculate the third current by just having the knowledge of Ia and Ib, and the field current, all currents can be measured by using Hall sensors. So, we have the Hall sensor to measure Ia, Ib and If. So, with this information we need to find out what is the torque angle. Now, we have seen that the torque angle is the angle between the stator flux linkage and the d axis. Now, this is the d axis. D axis is same as the pole axis. We are having the field in the rotor, the field is moving away. The d axis is of course not stationary, it is also moving away. It is moving at a speed of the rotor. So, this is the rotor speed. So, d axis is moving away with the speed of the rotor. So, what we do, we find out the component of this flux linkage along the d axis. So, we can find out the component of this along the d axis. So, we can project this along the d axis. So, this component is called psi ds, the stator flux linkage in the d axis. Similarly, we have a q axis, and the q axis is orthogonal to d axis. This is the q axis, which is having a right angle or pi by 2 with the d axis. And again we can project the stator flux linkage along the q axis. So, if you project the stator flux linkage along the q axis, this flux is called psi qs, or the flux linkage in the q axis. So, if we know the individual component psi ds and psi qs, psi ds is the flux linkage in the d axis, psi qs is the flux linkage in the q axis, we can find out what is delta. Delta is this angle, right. So, if this is psi qs, this is also psi qs. This angle is also 90 degree, all right. So, we can calculate delta provided we know psi ds and psi qs. So, delta is calculated by what is called a torque angle estimator block, and we can say that delta is equal to tan inverse of psi qs by psi ds. So, to find out delta, we should have information about the q axis stator flux, that is psi qs, and also about the d axis stator flux, that is psi ds. So, how to find out this psi ds and psi qs? Now, to find out this, let us remember the equivalent circuit of the synchronous machine in the respective axis. So, we have already seen the equivalent circuit in D and Q axis. So, let us try to derive this equation or this psi ds and psi qs from the equivalent circuit. So, if you take the D axis equivalent circuit, so what we have here, we are having a back EMF and a resistance drop, a leakage inductance, then we have the magnetizing inductance here in the D axis, and then we have the leakage inductance of the damper winding, the resistance of the damper winding, and then we also have the field winding leakage and the field winding resistance and the field winding voltage. So, this is our VDS, is the applied voltage, and this is the stator resistance, the stator leakage inductance, that is LLS in the D axis, and this is the magnetizing inductance LMD in the D axis, and this part is the damper leakage inductance is LLKD, damper resistance is RKD, the field leakage is LF, and the field resistance is RF, and the field applied voltage is VF. All right. So, these are the variables that we have here, the parameters, and we have the current in this case. This is the D axis stator current IDS. This is the damper current in the D axis entering this junction, that is IKD, and this one is the field winding current, that is IFD. So, we have to find out what is the magnetization current, and the magnetization current in this case in the D axis is IMD. So, we are talking about a salient pole machine. So, we have drawn the D axis equivalent circuit. Now, we have to find out the stator flux linkage. The stator flux linkage is the flux linkage associated with the magnetizing branch and the stator leakage. So, this is psi ds. So, psi ds is the flux linkage associated with the magnetization branch and also the stator leakage inductance. Now, to find out this psi ds, we have to find out what is IMD. IMD is produced by three currents. IMD is the magnetization current in the D axis, which is produced by the stator D axis current, the damper D axis current, and also the D axis field current. So, in fact, we can say that this IMD is basically produced by these currents, and of course, we do not know what is the damper current. The damper current is the current which we cannot measure. We can measure the field current because field is available, the terminals are available, so we can have sensor to measure the field current. We can also measure the stator current, we can also have sensors in the stator to measure the stator current, but unfortunately we cannot measure the damper currents. Damper currents are hidden inside the machine. Damper is a part of the field, the rotor, and the damper currents are not available for measurement. So, we have to somehow get the magnetization current in terms of the field current and the stator current. So, what is IMD? So, if you want to find out what is IMD, we can take this circuit. We can take only this part of the circuit. This is LMD. So, we have the current which is entering here is IDS, the current which is entering from this side from the field is IFD, and the current which is coming from the damper, of course the damper current is not known, so we will just replace it by the damper parameters. This is RKD and this is LKD, and this current is IMD. So, we need to find out what is IMD in terms of IDS and IF. So, we can apply this basically a current divider circuit. So, we have the current, which we have the two currents here, and the currents are IDS and IFD, the stator current and the field current. They are basically divided partly in the magnetization branch and partly in the damper branch. So, we can find out this IMD in the following way: RKD plus LKD P divided by RKD plus LKD plus LMD into P. This small p is the derivative operator. This is d by dt. So, this dynamic equation will give us IMD by simple current division principle. So, if we know what is IMD, we can find out the stator flux linkage in the d axis. So, what is psi ds? Psi ds is given as LLS into IDS plus LMD into IMD. So, if you want to find out the stator flux linkage, we have two terms here, the leakage flux, that is LLS into IDS, and then plus LMD into IMD. So, this we can simplify and expand this, that is LLS into IDS plus RKD plus LKD P divided by RKD plus LKD plus LMD P, and then we have got LMD here, again we have to multiply with LMD, and then the currents will be can be written here. We can write the current, and the currents are IDS plus IFD. So, this is the expression for psi ds. Now, we can see here to find out psi ds, we have to know IDS. IDS can be measured by having Hall sensor. We can measure IA, IB, IC. If you know IA, IB, IC, you can transform that into D and Q component in the rotor. So, we can have IDS and IQS. So, in fact, IDS and IQS are measurable. So, we have got information about IDS. The field current IFD can be measured by having a sensor in the field circuit. So, we know IDS and IF, and the parameters of a machine are given. We know the stator parameters, stator inductance, we know the magnetizing inductance, we know the damper parameters. So, we can find out psi ds by this equation, and this equation all quantities are known, the parameters are known, the currents are also known. Now, similarly, we can calculate the stator flux in the q axis. So, I will just draw the q axis equivalent circuit. Now, this equivalent circuit is actually in the rotor reference frame. Even this one also is in the rotor reference frame. So, here exactly in the same way we have the back EMF in the q axis, the stator resistance in the q axis, the stator leakage inductance, then we have the magnetizing inductance, and then we have the damper parameter. In the q axis we do not have any field winding. The field winding is only present in the d axis. So, in the q axis, in the rotor we only have the damper winding. So, we can have the damper leakage inductance and we will have the damper resistance. So, this is IKQ and this is LLKQ, damper leakage inductance and damper resistance, refer to the primary side, refer to the stator. Then here the magnetizing inductance is LMQ in the q axis. The stator leakage inductance is in fact same because the stator is a symmetrical stator having 3 windings which are symmetrical. So, we have same leakage inductance in the stator, that is LS. Stator resistance will also be the same, that is RS, and this is the applied voltage in the stator VQS. Now, similarly the current entering here is IQS, and this current is the magnetization current which is going in the magnetization branch, that is IMQ. So, if you want to find out what is the q axis stator flux linkage, we can do that by this equation. Psi QS is equal to LLS into IQS, the leakage flux plus the magnetization flux, which is LMQ into IMQ. Now, again in a similar fashion, the stator flux linkage in the q axis is the flux linkage associated with the magnetization branch and the stator leakage. So, this is psi QS. So, this is basically given by this equation. Psi QS is equal to LLS into IQS, that is the leakage flux in the q axis, plus LMQ into IMQ, that is the magnetization flux in the q axis. The summation of the two gives us the q axis stator flux linkage. Now, how to find out IMQ? Similarly, we can do that as we have done previously. We will draw only this part of the circuit. This is LMQ and this part is the damper part, and the current which is entering this particular branch is IQS, and this current gets divided into two parts. One is in the magnetization branch, other is in the damper circuit. So, we are only interested in IMQ. Now, this is a current divider circuit. We have two parallel branches and the current will be divided in inverse proportion to their impedance. So, we can calculate what is IMQ. IMQ in this case can be given as, this is LLKQ, the leakage inductance, the resistance RKQ. So, we have RKQ plus LLKQ P. P is the derivative operator, divided by the total impedance of both the circuit, IKQ plus LLKQ plus LMQ into P into IQS. So, this basically gives us the magnetization current in the q axis. So, once we get the magnetization current, we will be in a position to find out the total flux linkage in the q axis, that is psi QS. So, psi QS in this case is given as RKQ plus LLKQ P divided by RKQ plus LLKQ plus LMQ P, and we have to multiply with LMQ because we are talking about the flux linkage into IQS plus the leakage flux, that is LLS into IQS. Now, if we analyze this expression for PsyQS, we see that in the PsyQS expression, in the right hand side, all the variables are known. The current IQS can be measured by having a Hall sensor in the armature. We can measure the various currents, IA, IB, IC, and once we measure the 3-phase current, we can transform the 3-phase current into the rotor reference frame into IDS and IQS respectively. So, in fact, IQS is measurable, and the parameters of the machine, like the damper parameter in the Q axis, the leakage inductances, these are all available to us. So, in the right hand side of this equation, all the values are known, so we can find out what is PsyQS. So, we have already seen the calculation of PsyDS. Now, we have been able to derive the expression for PsyQS. So, these basically two are dynamic equations. So, given the currents and the parameters, we can find out the flux linkage. And from the flux linkage, as we have already seen, that we can calculate the value of delta. Delta is the torque angle, and that is equal to tan inverse of PsyQS by PsyDS. So, this is how we implement the block torque angle estimator. All these calculations are done in real time. Of course, if you see this expression for PsyDS and PsyQS, we will see that ultimately we have to implement a few integrators. P is the derivative term, so we have a P in the numerator and also a P in the denominator. So, ultimately this will lead to something like an integrating action finally, and then we have a summation in this case. So, there is no derivative term in the final implementation of PsyDS and PsyQS. So, once we find out PsyDS and PsyQS, we can calculate the torque angle delta, which can be used for control of synchronous motor. Now, we have also seen that in the synchronous motor control, we also need theta r. Theta r is the rotor position. Rotor is moving away. The d axis is moving away. The rotor is a continuously rotating member. And then also we need the expression for the speed. And these theta r and the speed are obtained using an angle resolver. Angle resolver stands for AR. AR is the angle resolver. So, the angle resolver gives us an information about theta r and omega r. Now, what is an angle resolver? Traditionally, angle resolver actually gives us the cos and sine angle of the rotor. But nowadays, we have availability of incremental encoders and also absolute encoders to implement this angle resolver. So, we have two types of encoders. The encoders are, we are actually discussing about the angle resolver. That is AR. So, this can be, the objective is to find out theta r and omega r, and this can be obtained by using incremental encoder. The incremental encoder gives us pulses as the rotor rotates. So, it gives us train of pulses like high and low signal like this. So, this is the output of an incremental encoder. In fact, this incremental encoder actually gives us two signals which are in quadrature. So, this is one channel, and the other channel of the encoder will basically gives us again a train of pulse, which is basically shifted from the other pulse by pi by 2. Okay. So, this is, maybe we can call this to be x pulse, this will be y pulse. So, these two are the output of the incremental encoder. In addition to that, encoder also gives us another signal called a marker pulse. Marker pulse comes once in a revolution. So, this pulse just gives us one pulse in a revolution like this. So, this is may be the signal called Z. So, if we use incremental encoder which is not very expensive, which can be very easily mounted on the rotor, we will have 3 signals x, y and z, and in this case x and y are in quadrature. So, depending upon the rotation of the rotor, the direction of the rotation, x may lead y or y may lead x. So, by counting this number of pulses, we can get the information about theta r. So, theta r can be obtained by properly counting the number of pulses coming. Out of the encoder, let us say x. So, if we take one signal, let us say x, if we count the number of pulses, we will be able to have an information about theta r. Now, what about the direction? The direction can be obtained by seeing which pulse is leading which one. So, the direction information can be obtained by simply by a D flip flop, which can be used to find out whether x is leading y or y is leading x. The direction of rotation can be obtained by finding out the phase angle or the lead lag information between x and y. And what is the role of the marker pulse? The marker pulse, actually when we are continuously incrementing and trying to find out theta r, angle actually cannot be higher than 360 degree. When we are talking about one revolution, it is 360 degree mechanical. So, 720 is same as 360. So, in fact, this marker pulse actually synchronizes the signal so that the cumulative error is reduced. So, marker pulse gives the indication of a start of the counting, and this is also used to synchronize so that the cumulative error in the counting is made 0. So, the marker pulse Z is used to make the cumulative error in counting 0. So, this is about incremental encoder, which is not very expensive. Now, if you want to find out the exact theta r irrespective of the rotation, we can go for what is called an absolute encoder. It is expensive, and absolute encoders are available either in the binary coded form or in the gray coded form. We can have the option to choose whether to go for a binary coded form or a gray coded form. So, the absolute encoder will give us a unique combination of the pulses so that we can find out the value of theta r. So, the second option is to go for absolute encoder. They can be either 4-bit, 8-bit or 12-bit. So, what we are getting in this case, we are getting 4-bit at a time, or we are getting 8-bit at a time, or we are getting 12-bit at a time. So, when we are getting multiple bits at a time, this combination of the bits will give us an information about the rotor position. Since we have a large number of wires, it is naturally expensive. So, they are actually preferred for those applications where the absolute encoders are really very necessary. So, in this case the combination of bits gives the information about theta r, and once we find out theta r, we can differentiate this information at what rate theta r is changing, and d theta r by dt will give us omega r. So, after finding out that, we can calculate this omega r by having this expression that delta theta r by delta t is the rotor speed, that is omega r. So, this is all about angle resolver. So, the angle resolver is an essential part of synchronous machine, because without this angle information a synchronous motor cannot be controlled. It can only be controlled provided we have some angle information. So, we are discussing about the control of synchronous machine. So, we have seen how we can implement the torque angle estimator and also an angle resolver, and synchronous motors are usually controlled in closed loop fashion with a rotor position feedback. We will go to a new topic that is on permanent magnet motors. So, these permanent magnet motors are very widely used for various applications. The reason behind their popularity is the compactness. So, today we will be discussing about permanent magnet motors. They are popular because of high torque to weight ratio. The field winding is replaced by a permanent magnet, and hence we do not have any field excitation. The permanent magnet gives the flux, and the armature is the conventional armature, and there is interaction between the permanent magnet flux and the armature current, and hence a torque is produced. Now, if we see the classification of these permanent magnet motors, essentially we have two types of permanent magnet motors. The first one is the conventional permanent magnet DC motors, where the armature is a rotor and the field is the stator. The field winding is replaced by a permanent magnet. So, number one, types of permanent magnet motors. The first type is conventional DC permanent magnet motors. Now, in this case the armature and the commutator segments and the brushes are just like that of a normal DC motors, but the field windings which are in the stator are replaced by permanent magnets. So, we have the armature here, we are having the brass in this case, but instead of a wound field, what we have here, we have a permanent magnet field. So, this is the structure of a permanent magnet DC motor, the conventional one. So, we have the armature and we have the field winding. The field winding are having permanent magnets. These are the permanent magnets in the field winding. Okay. And when we mount this permanent magnet, basically the magnet comes in piece, and this is north south, and this basically these are the pole shoe, and similarly here we have the pole shoe and the magnet is placed here, we have south and north. So, we have two magnets, and one gives the north pole, other gives the south pole for the working of the DC motor. Now, this type of motors are also very popular for low power and medium power application. we also have another type of permanent magnet called brushless DC motor and also permanent magnet synchronous motor. Second type of permanent magnet motors are brushless DC motors and permanent magnet synchronous motor, and that is called PMSMs. So, these two types of motor like brushless DC motor and permanent magnet synchronous motor, the construction is somewhat similar to that of a conventional synchronous machine. In the synchronous machine, the field winding is on the rotor, the armature is on the stator as we already seen, but the field winding is replaced by a permanent magnet field. There is no winding in the rotor, there is no field winding in the rotor. Instead of the conventional field winding, we have the magnets, the permanent magnets in the field winding. Now, before we talk about the details of these permanent magnet motors, let us have some basic idea about the working of these permanent magnet motors and something about the material, the permanent magnet material. So, we will see the principle of permanent magnet motors. In fact, we can discuss about principle of permanent magnet material. Let us take a permanent magnet material. Let us take ring shaped permanent magnet material and let us cut an air gap. So, we will take a ring in this case, and then what we will do here, we will cut an air gap. So, this is a permanent magnet, maybe an iron material, and then this is having an air gap which is of length Lg, and this is having a circular cross section, and the cross section, this is the iron part and this is the air gap. And the length of the iron part is Li. So, this is the length of the iron part from this side we have Li, and the cross section area here is Ai. Similarly, the length of the air gap is Lg and the area of this air gap is Ag. So, usually when we talk about a magnetic material, they follow what is called a BH characteristic. So, if you see the BH characteristic of a typical material, this is the H is the field strength, which is usually the unit is ampere turn per meter, and the flux density is B and the unit is usually Tesla or Weber per meter square. Tesla is same as Weber per meter square. So, if we plot the BH characteristic, we have various types of material. We can have a soft material, we can also have a hard material. So, if we plot the BH characteristic, it starts like this. As we increase the H or the field strength, the flux density increases. Then after some time it saturates. With the increase of the field strength H, the flux density no more increases, and then if we decrease the field strength, the flux density decreases but in a different path. And then if we make H negative, flux density further decreases and sometimes this becomes equal to 0. Then we further increase H in the negative direction, it reverses. So, B becomes negative and then we increase H after that. So, H will increase to 0 and then H will become positive. So, this is how the path is traced, and this is what we call a BH characteristic. Sometimes if we see that some of the material have got very small BH loop, and in this case if you see that the reverse path and the forward path, they do not coincide, and the loop inside this two paths enclosed is called the BH loop. In a soft magnet, this BH loop is quite small. In hard magnetic material, the BH loop is quite large. So, in this BH loop we have got some important property. This is called BR. BR is basically the flux density for H equal to 0. This is called residual magnetism or remnant magnetism. So, BR is called residual magnetism or remnant magnetism. All right. And then when we make H negative, B becomes equal to 0, and the value of H for which B becomes equal to 0 is called SC. SC stands for the coercive force. SC stands for coercive force. So, we have BR. BR is the residual flux or the residual magnetism, and SC is the coercive force. So, these are the two important quantities of a magnetic material. So, in this particular loop, we have loop structure, a circular permanent magnet, in which we have caught an air gap of length Lg. Now, in this case, you know that we do not have any current. So, since we do not have any current, we can say that the total ampere turn is equal to 0. If you take this magnetic path, we have partly iron and partly air gap, there is no exciting current. Even if we have a coil here, the coil can be thought of, we can have a coil like this and the coil is not carrying any current. Now, in the absence of any external current, we can say that total ampere turn drop in this loop is equal to 0. So, we can say that the total ampere turn is equal to 0. Now, that will give us this equation that the ampere turn in the iron is Hi into Li. Hi is the field strength in the iron and Li is the length of iron plus Hg Lg. Hg is the field strength in the air gap and Lg is the length of the air gap, that is equal to 0. Or we can say that Hi is equal to Hg Lg by Li with a minus sign. So, we can say that Hi is equal to minus Hg Lg by Li with a minus sign. It is a negative quantity. So, now again we can say that whenever we have a loop, the flux will be the same. We have the same common flux because the same flux is passing through this loop. The flux lines are basically passing and they are crossing this and entering. So, the flux lines are basically closed line. So, whatever flux is in the iron, the same flux is also passing in the air. So, we can say that we have a common flux here. So, what is flux? Flux is flux density into the cross sectional area. So, we can say here that phi is equal to Bi into Ai. If the flux in the iron is Bi into Ai, flux density of the iron into cross sectional area of iron is equal to Bg into Ag, the flux density of air gap into the cross sectional area of the air gap. So this is the flux passing in that particular loop. Now we can say that what is Bg? Now Bg is equal to Bi Ai by Ag. All right. So Bg is equal to Bi Ai by Ag. Now we know that mu naught is equal to Bg by Hg. Hg is the field strength, Bg is the flux density, and they are related by a constant of proportionality called permeability constant. So this is mu naught is a constant of permeability of free space. Since we have air gap there, it is mu naught. So mu naught is equal to Bg by Hg. So we will replace this Bg in the following fashion, that mu naught into Hg is equal to Bi Ai by Ag, or we can say that Hg is equal to Bi Ai by Ag by mu naught. So this is what we have here. Now this Hg we can take from this equation and replace it in the previous equation. In the previous equation we have one Hg term here. Now this is our Hg. Now this Hg we can replace by what we have here is Bi Ai by Ag by mu naught. So we can say that that's equal to minus Bi Ai by mu naught by Ag into Lg by Li. It's an interesting equation where we have Hi equal to minus of Bi Ai by mu naught, Ag into Lg by Li. Now if you see the right hand side, in the right hand side we have the flux density Bi, Ai the cross sectional area, Lg, Li, Ag. So these are all positive quantities. The area is positive, the lengths are positive, the mu naught is positive. So we are seeing that Hi and Bi are opposite sign to each other, and hence in a material where we have an air gap, the characteristic operates in the second quadrant. So this is basically the second quadrant where Bi and Hi are of opposite side. So in all permanent magnet motors, they operate in the second quadrant where Bi and Hi are of opposite side. So in the next lecture we will see how we can take a specific permanent magnet material and how we can construct the field winding or the field and the stator. That we will be discussing in the next lecture.